Okay, so let's talk a little bit about linear modeling. So most of this is probably pretty familiar. But some of the language the book uses, like this word modeling, is like looks kind of scary, but it's kind of the only thing about modeling is the point of view is like you have these data points, and you have some function that ideally you would like the function to exactly describe your data set, and maybe that happens, maybe it doesn't. We use the word modeling when it's like when we think about maybe we have something in real life and we just are trying to describe it using math, and maybe it's valid, maybe it isn't. It just really depends on if the data is like super duper well behaved or not. So let's just start graphically here. I use black points to like imagine we have actual data points. That's very nice and exactly along the line. Well, I drew a blue line. Every time I had 2 points on the graph, I drew a blue line in between them, and well, just one blue line hits all the data points, and that's all it means for your data set to perfectly fit a linear model. So for some things like physics, under sort of idealized circumstances, maybe you can sort of get this or close enough to it. Yeah, like usually stuff like how much gasoline you get per dollar, for a certain amount of money spent, stuff like that is, things in nature tend to be a little bit variable. So this is maybe hard to get in real life, but if it does happen, that's what the picture looks like. And then not linear is just you draw a line between 2 points, and maybe even 2 or 3 points are on the same line, maybe 3 or 4. But if there's even one exception, then then the output y is not strictly described as a linear function of x. So it's just you tried to fit all of the data to a line, and there was at least one point that was not on your line, and then if you draw, and that means that, well, if you took one of the points, like you have this line here, here's a point that it misses at x equals 4, it goes through the ones at x equals 2 and x equals 3 just fine, but it misses that, this line misses that point, and well, we draw another line, well, there's, once you miss a point, then it's like you have to draw a different line that's going to miss that other point if you try to, you just can't do it. And that's kind of all there is to it. For some problems, it might start with the data set, so you won't really know until you actually draw the picture. For the homework, I'm having you go ahead and compute the lines, and then there are 2 different formulas for figuring out an equation of a line. So the point slope formula is kind of the fastest. Well, first of all, you have to have the slope. So the slope is just change in y divided by change in x. Just make sure that, well, you have 2 different points on your graph. You're trying to fit a line through it. And it doesn't matter what you call them. Just make sure that point number 1, they both get the minus, and then point number 2, just as long as there's 2 different ones, and then these 2 are matched up. So it's your first one minus your second one, first one minus your second one. So, and then y is in the numerator, x is in the denominator. So it could be x3 minus x0 in the denominator, but then it would be y3 minus y0 in the denominator. So whatever you want to call them, you have 2 different points in mind. I think the book uses numbers 1 and 0, but I labeled them 0. Earlier I committed to this labeling, so let's just make it consistent. You have 2 different points on the graph. If we use those 2 points to construct a linear model, well, maybe all of the data fits and maybe all of it, or maybe there's a problem. Let's see what happens. So first we find the slope, and then that number goes into the point slope formula. The point slope formula is you have a point on the graph, x0, y0, and this is the point that I labeled x0, y0. So y0 is 0, x0 is -2, so we get to be careful about the double negative, we get to be careful about this parenthesis, so we distribute the 1/2, and we get y is equal to 1/2 x plus 1. All right, so it doesn't really, I could use this one instead, and I should get exactly the same result. So there's a couple different ways you could check this. The fastest way to check it is you would just plug in all the x values and make sure you get the correct y value. So if I plug in -2, I get y is equal to -1 plus 1, which is 0. So that fits the linear model. We plug in 0, and then we get y is equal to 1, so that fits the linear model. We plug in 2, we get +2. Perfect. We plug in 4, we get 2 plus 1. 2 plus 1, which is equal to 3. That's also perfect. So just plugging in all of the x values and making sure you get the correct y value. That's one way of checking your answer. The other way, well, I'm just making sure you get a lot of practice drawing diagonal lines. So this is sort of a longer way to check, but it does give you more practice finding equations of lines. So let's just repeat this process and see if we get the same thing or not. So we should, because we just saw that one line is going to fit all the points, and it doesn't matter which 2 points you pick, you should get the same thing. But let's just try this one right here and this one right here and just see that we get the same thing. So sure, let's do that. So let's try those 2 points. And I'm going to erase this stuff. So if you want to look at the first thing we did, you can pause for a second, but I'm going to erase a little bit. Okay, so the final answer is I'm claiming that if you use a different point, follow the same process, you'll get exactly the same answer. That's what's whenever it's actually a perfect line. Well, I lost it anyway, but you can rewind if you want to see that. Okay, it's hard to erase just one thing like that. Okay, so let's see if we get the same thing. So this time we'll use I have 0.3 and we have 0.1. So the point number 3 was y was 4. Or sorry, x was 4. Sorry. Change in y was 3 minus 1. Change in x is 4 minus 0, so we get 2 divided by 4, which is indeed equal to 1/2, so that's the same as previously. Then we have y minus whichever point we want. Let's do, doesn't matter, y minus the third point equals slope times x minus, again, the third x value. So point slope formula, we get y minus 3 is equal to 1/2 times x minus 4 distribute the 1/2. So 1/2 of -4 is -2. So y equals, we add 3 to both sides. We get 1/2 x plus 1, which is exactly the same as the thing that I accidentally erased because I got it with the spray bottle a little bit. So So that's it. If I give you these 4 points and I ask you to find a linear model, or if I ask you to find a linear model that fits these 2 points, or these 2 points, or these 2 points, well, if I ask you to do it and repeat your work, then you'll get the same answer every time, because the one linear model in slope intercept form is universally valid for everything. On the other hand, if I give you something like this, where it's not perfectly along a straight line, then that's not linear, and then either I ask you to find one line using whichever, maybe these 2 points, and then you try to plug in all the x's, and then this line fails to fit these 2 points. So even if there was a third point way out here, it's still not linear because it's not perfect. It has to fit everything, or else it's, from the point of view of algebra, y is not perfectly modeled as a linear function of x. So that for the point of view of algebra, that's the end of the story. All right, so I'll make a separate video for the next thing, I think. So there's just one other thing I want to say, but for the algebra problems, this is all we're going to do with it. So I want to sort of leave it at that. But if you're curious, I want to talk a little bit about statistics, but it's in statistics class they talk about that a little bit more. So I'm going to leave it alone for now.